Howdy, everyone. Happy sunny Friday. I hope you're all doing okay, and I hope you found the exam on Wednesday to be okay. This cartoon shows this poor guy trying to count the number of stars, obviously, and that's a huge task, of course. What we see in the normal sky is far less than 1% of all the stars that are out there. It might even be less than a thousandths of a percent. I've been telling you that the estimates now are that there are 2 trillion galaxies, and the larger ones have 200 or 300 billion stars in them. And these numbers just come from estimates from the Hubble telescope by focusing in on a very small region of the sky for a long, long time, and then making the assumption that there are a similar number of galaxies all around. Uh, I mentioned to you the James Webb telescope, which will follow up on the Hubble. The latest launch date is now Halloween of this year, so let's hope that goes off. Many people estimate that this could be 10 to hundreds of times better even than the Hubble. And the biggest part of the James Webb telescope is it's going to be focusing in into the infrared region. You remember we've talked about the Doppler effect of how it shifts frequencies to lower values. So instead of looking at things in the visible, we're now looking at lower energies in the infrared. And so that will allow the telescope optimistically to look at the first 100 to 200 million years after the Big Bang. So stars were just barely beginning to form at that time. So we have somebody very excited about that. That's very good. Okay, so we're in the middle of talking about molecular structure. Mostly we have talked about diatomic molecules. Just as a quick reminder, this was our scheme that we had when we looked at a lot of homonuclear and almost homonuclear diatomic molecules. And the main purpose of our looking at this was to emphasize the points that we get the best bonding if we have a good match of energies and orbital sizes and so on. And we also got a picture of what sigma bonds look like and what pi bonds look like. We then talked a bit about HF. Here is the diagram for HF. And so this is still diatomic, but you'll notice it's very different. We're combining the 1s orbital on hydrogen with a 2p orbital on fluorine. And so our orbitals wind up looking like this. This is the bonding orbital. The hydrogen is here. Here's the center of the fluorine. And we bring the plus wave functions up, and we create a sigma bond that looks like that. Anytime we start from 2 atomic orbitals, we have to generate 2 molecular orbitals. One is typically bonding, like this one, and then the other one is antibonding. Antibonding occurs when you have to create a node plus wave function going to minus wave function. And I also pointed out that there are some combinations that just don't work. And so the 2py and 2px orbitals would go sideways to the hydrogen and not create any bonding. We then talked quite a bit about lithium hydride, and still a diatomic molecule, but it showed already that when you have more than one type of orbital on each atom that can bond, you can sort of get combinations that organic chemists like to call hybrids. And I've contended that we really don't have to talk about hybrids. We could go directly from the atomic orbitals that we have, throw all the possible orbitals into a pot, and then get the ones that are generated. But for our purposes, last Monday, then we said, let's create a couple of hybrids, and then we can understand why there's kind of an orbital left in the middle. So we created one hybrid pointing towards the hydrogen that created the lowest energy orbital. But then the hybrid pointing in the other direction uh, really wasn't able to bond to anything. And so it didn't change energy from the hybrid point. But an important point I wanted to make out was this was not really an SP hybrid. It was a lot more S character than P character. And if you look back in your notes, you'll see I gave you quantitative values for these. And then, one more thing. If you look at this diagram, if you look at the molecular orbital that's formed, its energy is closer to the energy of the 1s orbital than it is to the 2s or 2p orbitals of lithium. And consequently, the weight function is going to have much more contribution from the hydrogen than the lithium. And it turns out, we contend, hydrogen is more electronegative than lithium. And so when we wind up looking at this system, we would say it's Li delta plus with a partial plus charge, hydrogen minus. Generally, we're used to having things like H plus F minus, but here the hydrogen tends to be more electronegatives. In freshman chemistry, you would have learned about electronegativities. You would have been told that for hydrogen it's 2.2, lithium it's 0.98. The larger number demands that you get more electrons attracted to that. And just to remind you where this would come from, we talked about shielding for atoms. Here's our lithium atom. So these are electronegativity values now, but it's a low value for 0.98 because this electron is held pretty tight by almost well, it's only about a plus one charge, 1.4 or something like that. But for fluorine, you have a lot of these outer electrons that don't shield each other very well, so you get a high electronegativity. And into your notes, I also just stuck in some electronegativity scales. Commonly used one is the Mulliken scale, where you just average the ionization potential and electron affinity. They both result from how much charge you have in the nucleus and how much shielding you have. Electron affinity, if you've forgotten, is the ability of an atom to attract electrons. So again, if you have a high positive charge, high effective positive charge, then a lot of electrons want to get attracted to it. Okay, but now, I showed you this last time, but I want to emphasize this again. Hybrids are artificial creations, and it helped us in the case of lithium hydride. We could draw the two hybrids, and we could say one combination of S plus P made an sp hybrid, and it bonded to the hydrogen. But as I showed you in the quantitative parts, it had a lot more S than P parts. But it was useful in looking at it. Okay, so hybrids are artificial creations. Molecular orbitals are real orbitals that are created by combinations of atomic orbitals. We say these are LCAO, linear combination of atomic orbitals. And so in the lithium hydride case, we could have this either be a p orbital or kind of like an sp hybrid bonded to hydrogen. And then this would be our molecular orbital where the electrons go. And I also wanted to emphasize how stories about sp3 hybrids, sp2 hybrids, and so on tend to fall apart when you get very different atoms. So my favorite example is methyl chloride. Methane with all hydrogens, all the bonds are equal, and each one has 1/4 contribution from an s orbital, 3/4 from p orbitals. But when you go to methyl chloride, the carbon-chlorine bond is almost totally just p orbital. And so there's very little p left to share with these hydrogens. Hydrogens, like s orbitals, they really want to claim the carbon s orbital for itself. And last example I wanted to give you is you learned in organic chemistry about acetylene having sp hybrids. Again, it's a nice model. It shows you why the molecule should be linear. But notice that this sp hybrid I'm drawing on the carbon here, pointing to the hydrogen on the right, is going to be very different from the one pointing towards the left. The one pointing towards the right wants to bond to a hydrogen s orbital, and so this will have a lot more s character than the other bond. The carbon-to-carbon bond, carbon is perfectly happy to mostly use p orbitals. So even though this gives you the right geometry, it's really not a correct representation to say that you have sp hybrids. And just as a reminder, in acetylene, you also had two sets of pi orbitals like this. Okay, so let's now start looking at larger molecules. And you'll find in your notes that I'm utilizing some symmetry symbols. We don't have time in this course to get into giving you a background for symmetry, but basically the rule is that orbitals of the same symmetry designations, where they're called symmetry species, they're labels like A1, B1, B2, A1, they have to be the same to form bonds, and I will show you how that works. So again, ignore this so-called character table and so on, but let's just look at the orbitals that we have in water. So here are the oxygen orbitals we can use. We're not going to use the 1s orbitals, they're inner shell. 2s orbital looks like this. 2px will put in the x direction. 2py will have coming out of the screen. And then 2pz is an orbital that looks like this. There's a omission in your lecture notes. So what I should have here is this combination on the hydrogen atoms is 1s1 plus 1s2. When we start looking at bonding in larger atoms, you have to look at all of the equivalent orbitals simultaneously. So water has two equivalent hydrogen atoms, so we have to look at the hydrogen atom on the left at the same time as the one on the right. So we look at 1s1 and 1s2. And then we make combinations of these. Symmetry tells us how to make the combinations, but for the purposes of this course, I'll just tell you what the results are. So the hydrogen combinations are, we can add them together. We'll take plus wave functions for the two orbitals on the left and on the right. And then the other combination we're going to make is we're going to have opposite signs. So we'll have a 1s1 minus a 1s2. And I'm going to check the chat messages. We're asked if the second exam will be on the date of the syllabus. The plan is to keep it the same, but as I've said in the syllabus, dates could be flexible. So let's see how it goes. I would like to have it still on the same date because we still have to end the course at the same time. There's a question, do orbitals have to have the same N to combine? N means non-bonding, and I'll talk about that. They need to have the same, these labels A1, A2, B1, B2, they're called symmetry species. They need to have the same symmetry species. All right, so here is the molecular orbital diagram for water. The oxygen orbitals are on the left. I've neglected the 1s orbitals, they're inner shell, and they don't contribute to the bonding. So oxygen has a configuration 1s2, 2s2, 2p4. So we would start with 2 electrons here and 4 electrons there. On the right, we have the two hydrogen combinations. In my notes, I labeled it 1s1 plus 1s2, and the other I labeled 1s1 minus 1s2. Now these are drawn a little bit apart, but I'll put a bracket around them to indicate they're degenerate. On the atom, on the atoms themselves, they have exactly the same energy. Okay, well, to get the molecular orbital diagram, we then have to combine the correct symmetries over here with the correct symmetries on the left. So on the right here, I've drawn what the pictures look like. So our lowest energy orbital in water is going to look like this. We'll take a plus 1s1 on the hydrogen on the left, a plus 1s2 in the hydrogen on the right, and we will take a plus wave function on the 2s orbital on the oxygen. We smush these together, and this is what the bond looks like. Now, I'm going to say this over and over and over again, but realize, please, that orbitals are different from bonds. In freshman chemistry, it's kind of implied when you put two electrons represented by dots between two atoms, that those two electrons are a bond. That's not the case. So these two electrons, if you look at it in the lowest energy, this is this A1 orbital. So the picture here corresponds to the lowest energy here, has an orbital that includes both hydrogen atoms and the oxygen atoms. So the two electrons here will be traveling all around the entire molecule. They're not stuck in one single oxygen-hydrogen bond. So that's an important point. We're going to say that orbitals are delocalized. They're not on just one single bond. Okay, well, this is the strongest bonding orbital, or the one that gives us the strongest bonding. But we also have one labeled B1, and we get that by taking this 2px orbital that we have up here. It winds up having symmetry species B1. And then we combine it with the orbital combination on the hydrogen atoms, minus on the left, plus on the right. And this will give us the best bonding. We can have a wave function that overlaps with a negative sign on the left, and then a wave function part on the right with a positive sign. The node is going to be right on the oxygen atom. But also note that this allows the two electrons in this orbital here to travel back and forth between the two hydrogen atoms. So again, these two electrons are not isolated. Well, anytime we make bonding combinations like this one, we also create the anti-bonding one. And it's generally easy to figure it out because we just create a mismatch. So if we put a minus sign on the atomic orbital on the 2s for oxygen, you'll see the minus cannot bond nicely to the hydrogen plus combination. So this orbital stays pretty much like that, node in the center, and you'll see way up here is our anti-bonding orbital. So that orbital exists, but electrons hate to go into that because they destabilize the system. Notice that we're starting 2 electrons in the oxygen 2s and 4 electrons in the 2p, and then 2 hydrogen electrons up here. So when these electrons in water drop into these low energy molecular orbitals, we're stabilizing everything to a great extent. Everything in nature wants to go to its lowest possible energy. And so if hydrogen and oxygen can come together and put 2 electrons much lower in energy than they were in the atoms, we've gained a lot. Same thing true for this B1. It's not quite as stabilizing an orbital, but it still exists. Here's the anti-bonding B1 star. You can see I've just flipped the signs of the hydrogens. And so here's the B1 star anti-bonding orbital. Okay, now notice with the 2 P's, I had an A1, B1, and B2. I've used up the A1 from the P here, sorry, the S here. I've used the B1 from the P orbital. But I also have a B2 orbital on the oxygen, and there are no B2 orbitals that we have for the hydrogen atoms. So this is strictly non-bonding, and we would actually, in some diagrams, I'll show you, I'll just put an N next to it. I might put a sigma here for sigma orbitals, sigma star up here for anti-bonding, and then put an N here. Lithium hydride, you remember, was kind of weird because we had three orbitals from which we created two bonds and then kind of a orbital floating in between, which we said was mostly non-bonding. Water has an unusual case in that one of the p orbitals, namely the pz here, pointing down here between the hydrogens, it's capable of weak bonding. So its bond would look like this. And you can see that all the plus signs would match up, and so we could have a bonding interaction. The problem for this p orbital is the hydrogen atom orbitals have already mostly been used up to create this lowest A1 orbital. So this orbital can stick its nose in only a little bit to participate. So this isn't enough for us to say, well, this is really an sp hybrid, because it's at least 90% plus from the s orbital, but maybe that 10% is just enough to lower the energy of this p orbital a little bit. So this is the entire scheme. We'll put in the electrons that we needed to from the 6 we had for the oxygen, excluding the 1s, the 2 we had from the hydrogen. So these are the 8 electrons. So basically, you can see we have 2 bonding orbitals, one non-bonding and one slightly bonding. So for the 2 bonds that we're creating, we expect them to be single bonds. So you can sort of divide the number of bonds by the number of bonding pairs of electrons, and that'll give you what each bond is. For students taking inorganic chemistry, which chemical engineers typically don't, you're often taught about water being a ligand in transition metal complex. You might have a nickel with 6 waters attached to it. And what is discussed there, that this non-bonding pair of electrons can get donated to the metal. If you draw a Lewis dot structure for water, as I'm sure you must have in freshman chemistry, you would have had 2 pairs of non-bonded orbitals on your dot structure. But if you look at this diagram, one of those pairs of electrons are somewhat bonding, and so they're not as readily donated to a metal as this B2 orbital. So just by understanding this diagram, we learn a lot more about the properties of water and its ability to donate electrons. Water, of course, is arguably perhaps the most important molecule in the world, maybe oxygen close second or something like that. So it's important to understand the characteristics of water. Everything in the human body has water, and so the aqueous behavior of molecules is critical, and so it's important to understand this. One thing we'll also see as we talk later about electronic spectroscopy, this kind of diagram correctly predicts what the light absorption properties are of water. Water vapor is colorless, and that's because any electronic transition of electrons from one of these orbitals to a higher one is at an energy higher than the visible spectra. So the transitions take place in the ultraviolet. You can have a transition here from this A1 here to this A1 star, and that's way, way deep into the ultraviolet region of the spectrum. So maybe I'm trying to be cute, but if you go to Padre Island and you don't want to get a sunburn, if you go underwater and stay there, then the ultraviolet lights will get absorbed by the water above you, and you don't have to worry too much about the sunburn. But you can learn also about other transitions here. You can go from B1 to B1 star. That would be lower frequency in the ultraviolet. But there's a whole lot of information here. Now in our course, obviously I can't expect you to immediately learn everything that one would need to understand bonding from molecular orbital point of view. You'd also have to have a background in symmetry. But I'm just trying to give you some examples of what the nature of these are. I stuck this into your notes also. I'm not going to read this to you, but here's an attempt to draw the pictures of what these orbitals look like. I might note that the nomenclature here has the B1 and B2 reversed, and that's a result of which plane you put the water molecule into. But anyway, it's pictures of the orbitals. It shows the same kind of combinations. It also tells you what some of the energies of these orbitals are. So okay, we're starting here at 559 eV, I guess. But anyway, this shows it to be 28 electron volts above. An electron volt is about 8,000 wave numbers. So this is something like 23,000 wave numbers. 230,000 wave numbers, which is practically the X-ray region if you want to take an electron from the lower one to the upper one. Anyway, read this if you want to get some more detail. Okay, my notes again include symmetry aspects for this, but please just ignore what these are. Just appreciate the fact that we can generate what the symmetry combinations are for things like the hydrogen atoms. We can actually just read off from tables like this what the symmetries are of the carbon orbitals, and then we can see how we put this together. So this would be the molecular orbital diagram for methane. So methane is 1s2, 2s2, carbon is 1s2, 2s2, 2p2. We have 4 hydrogen atoms. They all have the same energy. I need to mute everybody if the noise continues, but let's hope that it stops. If we do the symmetries of the hydrogen orbitals, and I'll show you what they look like, they come out to be with symbols A1 plus T2. So the inner shell carbon 1s orbitals, we say, are non-bonding, so the energy does not change when we go to the methane molecule. The 2s orbital for the carbon wants to bond to a 1s combination of the hydrogen, and that's going to be our lowest energy orbital. Notice that we don't have 4 equivalent energy orbitals, as might have been implied when you learned about sp3 orbitalization, hybridization. So let me jump to the next page and just show you what this orbital looks like. So this is our lowest energy bonding orbital that we have in methane. So 2s orbital from the carbon, and then 1s orbitals from each of the hydrogens. And notice each one has a plus sign. So we're free to choose, but symmetry dictates which ones they have to be, which combinations have to be to give us the bonding. And once you see a bunch of these, you get to be able to predict what the lowest energy orbital is. And it's typically when you put all of the wave functions, the same sign, put them all together, and then this is your molecular orbital. So this kind of looks like an amoeba, but notice that the electrons would have probability of traveling all around the entire molecule from each of the carbon atoms to the other ones. And so that's what's represented by this orbital right here. So symmetry would tell us we use the A1 from here and this A1 combination from the 1s on the right. The p orbitals on carbon are triply degenerate, and I think you already knew that. Atomic carbon has 3 equivalent p orbitals, which one can call px, py, and pz. So they have exactly the same energy, but they can have different combinations to give you different symmetries. But they combine with a T2 set from the 1s, and we get 3 equivalent degenerate orbitals on methane. So I didn't draw them all out, but here's a picture of one of the T2 orbitals. There are 3 of these bonding orbitals. One is if we take the 2pz orbital pointing up, so the plus sign on the p orbital is up, the minus wave function is down. And then we match the hydrogen orbitals, so the plus wave functions go to the plus on the p, and the minus signs go to the minus. So this is the orbital that it looks like. I drew a terrible picture here, but I think you get the gist of it. The minus orbital comes out of the board and goes back into the board, and the plus wave function orbital is in the plane of the board. But notice this represents electron probability throughout the molecule. There are 2 other T orbitals, T2 orbitals that look just like these. One of these would have a p orbital pointing from the left to the right, and another would be coming out of the screen. But in each case, you would have 2 of the hydrogen orbitals with plus signs matching to the plus orbital, and the 2 minuses would match up to the minus. Notice if I turn this p orbital here and make it come out of the screen so that the minus orbital is out of the screen to the left and the plus goes to the right, then I would have to have for my molecular system, the hydrogens having a minus sign here and a plus sign here to make the whole business work out. Okay, so you can see this starts getting pretty complicated pretty rapidly. Key point is each orbital is not a bond. Electrons are delocalized. You actually get bonding orbitals and you get anti-bonding orbitals. Hopefully all of you can see that to get the anti-bonding orbital for this one, I would just change the sign in the middle for the 2s orbital to minus. And so it'd be a terrible match. All pluses all around, but a minus in the center, and that would wind up being the highest energy orbital. Okay, so back to the diagram. I showed you this orbital. I showed you one of the T2s. The other 2 come from the other 2 p orbitals on the carbon. And then here's a corresponding anti-bonding orbital, which I label A1 star. And then you'd have 3 corresponding anti-bonding orbitals. Again, one could study the electronic spectroscopy of methane here. Methane is also colorless. So if you have an electron jump from a T2 to a T2 star orbital, for example, it's in the ultraviolet and we can't see it. Okay, so I trust that might be a bit confusing, but maybe if you see a couple more of these examples, you get a sense of how this works. Now, some of you no doubt might be asking, well, what happened to sp3 hybrids? So notice that our 4 bonds come from these 4 orbitals that we have in the molecular orbital diagram. And so each one of those bonds is going to have 1 part s and 3 parts p for the orbitals. So calling them sp3 is a decent designation of telling you which atomic orbitals are involved in the bonding. But let's see what that does if we talk about hybridization and try to form hybrids. So typically when people tell you about sp3 hybrids, they give you a cube and then they point vectors from the center of the cube to 4 of the corners of that cube. And that would give you the structure of methane, and you can call each of those an sp3 hybrid geometrically. If we do this on an energy basis, and I want to create sp3 hybrids, and I want to create 4 of them all equal, then the energy here is going to be 3/4 of the way up from the A1 to the T2p orbitals that we have. So we would have 4 orbitals up here. So that's okay. But in order to apply what kind of bonding you get, we have to go to symmetry rules again, which sadly you don't get much chance to see anything about in this course. But when you apply symmetry rules, you find that the combinations of these sp3 hybrids come out to be A1 plus T2. Then when you combine them with the 1s orbital, again, the A1 comes out lower in energy. And again, it winds up looking just like this again. And then again, your T2 orbitals all wind up being the same energy, and then we get the same antibonding orbitals. So as far as quantitatively trying to understand the bonding of molecules, hybrid models really don't help. They help us get pictures and structures, but as I showed you with the case of methyl chloride, where the chlorine doesn't want to have sp3 hybrids, they can be somewhat misleading when you look at that. Okay, so you might have to digest some of this before you start getting a feeling for what's going on. And at the risk of making this even worse, you're absolutely not going to be asked anything about NO2. Fairly simple molecule, but nitrogen and the oxygen atoms have not only s orbitals, but all of them have p orbitals that can create bonds. So I'm showing you here the diagram out of a molecular orbital description book, and to show you what they are. And I hope your lecture notes aren't clipped off like my PDFs are here, but I think you can get a gist of what some of the bonding is. The lowest energy bonds we can think of as sigma bonds come from using the 2s orbitals on the nitrogen and on the oxygen. So remember, oxygen has Z equal to 8 protons in the nucleus, nitrogen has 7. So here are the 2s orbital energies for oxygen, here is nitrogen. You'll see nitrogen is quite a lot higher because the electrons see a lower effective charge. So a higher charge on the oxygen lowers these orbitals. But we nicely get 2 bonding orbitals. So here's one of them. This looks just like the one we have for water. Remember, we put s orbital plus s orbital plus s orbital. I actually mislabeled these. These should be, say, 2s and 2s. I must have been copying from the hydrogen where we have this combination. But it's a very similar looking lowest energy orbital. Then the other low energy sigma orbital comes from this. We put a minus hydrogen wave function to the minus lobe of the p orbital on the nitrogen, put a plus wave function to a plus sign here, and again we get something like this. Notice that basically we have 2 sigma bonds in the molecule, N to O and N to O, and we have 2 sigma orbitals. But each of these orbitals is not localized in a bond. Each of these orbitals involves the entire molecular structure, and so that's the characteristics that we learn when we look at molecular orbital theory. Here are the corresponding antibonds. If I mismatch plus minus plus, that's the 3A1 star. So my screen is a little bit foggy. Anyway, it's one of these higher ones that we're going to get as an antibonding orbital there, and we get a 4B1 star up there also. Now in this system, what makes it so very much more complicated, we can get pi bonding. So you can see this would be a nice pi bonding system where we the NO2 molecule, of course, has to all lie in one plane. If we have each of these atoms have one orbital come directly out of the plane, then we can form a p orbital like, a pi orbital that looks like this. And then the corresponding pi star orbital would look like this, plus minus plus. Whenever these combinations don't mesh nicely, then we get antibonding combinations. Some of these orbitals in between here are going to be pretty much non-bonding and they don't interact. And I don't expect you to be able to understand and follow all that. But again, I'm trying to give you just a flavor of what happens when we try to fully understand what are the characteristics of bonding in more complicated molecules. This isn't in your lecture notes, I think, but here's an example of what happens to octahedral metal complexes. It actually explains why many paints have colors. This dark arrow indicates electronic transitions, why cadmium-based paints tend to be yellow and things like that. So you can learn a lot from these diagrams. And here's the bonding of boron trifluoride. It helps explain why boron trifluoride is a good Lewis acid. It loves to accept electrons donated to it from molecules like ammonia. Okay, so this is in your notes. I'll put down hybridization a lot, but don't throw out everything that you learned from organic chemistry. Hybridization can still be a useful concept if you know which orbitals can be combined for bonding. So here are coordination numbers, and here are shapes. The things you learn most commonly in organic chemistry, it's tetrahedral sp3 hybrids. If you have things like ethylene, you can have sp2 hybrids. If you have molecules like acetylene, they can be linear and they would be sp hybrids. And there are many other combinations will predict the correct shape. And students in my other course who take the inorganic course, they'll see there's a lot of examples, including things like D2sp3, that's an octahedral structure. You can have DSP2s for strain structures and so on. So they can be helpful in understanding systems. So here are some cases. sp3 hybrids predict a tetrahedral. And if the substitution is not too severe, then more or less the structure will remain tetrahedral. So if you have CH3F, it would not be quite as bad as CH3Cl for distorting that tetrahedral structure. SF6 has D2sp3 contributions. In other words, 50% contribution from each p orbital, 1/3 contribution from each d orbital, 1/6 for each of these SF bonds. But the molecular orbitals that are going to come out for SF6 will look very different from what the hybrid might imply. I just showed you the diagram for BCl3. sp2 hybrids can represent that just as well as for organic molecules. And here's a case for more exotic molecules that inorganic chemists might run into. Okay, by my watch, we have about 5 minutes left, so we can just get started on our last topic for bonding. And I'm going to pick a case where something called the Hückel method approach, which works, and this applies to conjugated organic molecules. So just thinking about it, we're going to be talking, say, about the example of this molecule. If you properly learned about conjugation in organic chemistry, you would have realized that every one of the carbon atoms in this molecule lies in the same plane, and every one of the carbons would have an atomic p orbital perpendicular to the plane that's capable of pi bonding. So for the purposes of our example, I made this very highly complicated, conjugated, and we're going to see then how one can apply rules of bonding to understand what kind of structures and bonding we get in these systems. Ultimately, this all goes back to our initial discussion of H2 plus, diatomic molecular ion, and the H2 molecule. So you may want to refer back to the first few pages of our discussion on bonding to see how we set up the variation method. We wound up with a secular determinant, simultaneous equations, and so on. But I'll be reminding you of all that later in the week. But here are the rules for the Huckel method. Okay, we're going to assume that the interaction between 8 adjacent carbon atoms is beta. This is assuming that they're capable of pi bonding. It's going to turn out beta is something like minus 65 kilocalories per mole, or something like 270 kilojoules per mole. We're also going to assume when two atoms don't touch, when the two carbon atoms don't touch, that the interaction is 0. If you go back to our H2 derivations, we wrote integrals such as H11, H12, H13, and so on. Whenever we had a term on the diagonal of our determinant, we found that that represented the atomic energy of the atom we're dealing with. So in this case, this would be the alpha would represent the energy of the carbon atom, or the carbon p pi orbital, the one that's perpendicular to the plane of the molecule. So you use these rules to set up the secular determinant, and then this is what may mystify you, but I'll remind you about this next time. Then we're going to say, well, let's just say alpha, the energy of the carbon atom, is 0, and beta is equal to 1. Anytime we look at energy diagrams, we arbitrarily can pretty much decide where 0 is. For the hydrogen atom, you'll remember we said 0 was when the electron and proton were infinitely far apart. Here we're saying 0 is the atomic energy orbital on carbon. And we also are going to say beta is equal to 1. And mathematically, this means when we solve the problem, when we get a number like 3.4, that'll mean it's 3.4 in beta units. But this keeps us from having really ridiculous looking determinants that we have to work out. So if we apply this rule to the molecule here, and I don't have time to go over the whole thing, we basically start off just as we had for the hydrogen atom, alpha minus E. For the hydrogen atom, we had H11 minus E. Then here we had H12. So the first row refers to carbon atom 1, and then each column also refers to a particular carbon atom. So the first element refers to carbon atom 1, both as a row and a column. If we go to position H12, here, this represents the interaction between atoms 1 and 2, so we write this as a beta unit. 1 does not touch 3, so we put a 0. 1 does touch 4, so we put a beta here again. And then 1 does not touch 5 or 6, so we put zeros. And I'll review this then next time as we do it. But Here's a shorthand nomenclature, and I lost the bar that's needed for this determinant. You see I'm just throwing out the alpha, and I'm making each beta equal to 1. And even if we have to solve this problem with a computer, it's very, very much simpler to solve this determinant and wind up with this one where you have lots of things like beta cubes and beta to the fifths and things like that. So between now and Wednesday, you might want to see that you can convince yourself why we have the zeros where we do and where we have the betas where they belong. So each row represents a particular carbon atom 1, carbon atom 2, carbon atom 3, all the way through 6. And similarly, each column represents a particular carbon atom. And if we have two different carbon atoms, like row 2, column 3, this is position H23, that's a question of does carbon atom 2 interact with carbon 3? And we see it should, so we put a beta right here. Okay, well, hopefully when we go through this, this will give you better insight about conjugation and how quantum mechanical calculations will work in general when we look at molecular orbital systems. Your exam has not been graded yet. I think it's okay for me to go ahead and send you the answer sheet so you can have a sense of how you did. I would expect that the exam should be graded by Monday for sure. Any questions before we start?
Just one.
Yeah.
I think you mentioned that the exam will be graded with partial credit because I think I did a couple calculator errors,
Yeah.
and I'm not sure if.
Yeah. It's not unusual for someone to get more than half their points from partial credit.
Oh, okay. I was just checking on
Yeah,
that.
you don't have to have the right answer to get some credit.
Yeah, by the end I was rushing through it because it was getting tight on time. So I think I
Yeah,
did a couple calculator errors.
sure.
All right. Thanks, sir.
Okay.